You might already know a hyperbola that looks something like this. The idea of y equals 1 over x. But there is a general hyperbola case, and we can talk about it in the context of locus as well. If I had 2 points, A and B, let's put them here. My hyperbola is the locus of points where the difference between these 2 points is constant. My hyperbola is going to look something like this. And then if I were to draw lines that indicate the distance, let's make this line DA, and let's make this line DB. My locus is the collection of points P, where DA minus DB is a constant, but also where the distance from B minus the distance from A is the same constant. And we can see that in blue if I go from distance from point B and distance from point A. So you can see there's one line where the distance from point A is greater than the distance from point B, and there's another line where the distance from point B is greater than the distance from point A. And we used our concept of the modulus lines to say it could be A minus B or B minus A, but the fact is the difference between the two of them is going to be a constant. And that's the way we represent a hyperbola in locus form. Now you can also represent a hyperbola in Cartesian form. In Cartesian form, my standard form for a hyperbola that is centered at the origin is x squared over a squared minus y squared over b squared equals 1. And in this context, my a and b give me equations of asymptotes. So you'll see here, I could draw a diagonal asymptote here, and I could draw another diagonal asymptote here for this yellow hyperbola. The equations of my asymptotes will be y equals b over ax, which will be this line, with the positive gradient, or y equals negative b over ax, which is exactly the same line but with a negative gradient. And as our x values increase and increase, my yellow line, my hyperbola, will get closer and closer and closer to the asymptotes. So my equation is this, and my asymptotes are here. Now, if I were to translate that center point, which is here, up or across, I end up with an equation where I factor in my h, which is my across distance, over a squared, and I factor in my k, my vertical distance here, and that equals 1, and that should be squared as well. So ultimately, my translation will mean that my equation is slightly different, and of course, my asymptotes are slightly different. Rather than have a y, I'll have a y minus k equals plus or minus. You'll notice these are exactly the same except one's positive and one's negative. B over a, and then rather than x, I now have x minus h. So my general equation, if you will, for a hyperbola will be this one in light blue, where this is my line and these are my asymptotes. The specific equation that's centered on the origin is here. And finally, there are a couple of basic shapes for the hyperbola that we can look at. We've looked at a hyperbola that has an asymptote like this and an asymptote like this, and forms this shape. And that has the equation x squared over a squared minus y squared over b squared equals 1, centering at the origin. But I could also have a hyperbola that has asymptotes in a very similar position. But rather than go across, it actually goes up and down. So therefore looks something like this. And you've got to be very careful when you're drawing your asymptotic behaviour. This wouldn't be acceptable because you can see the line moves away from the asymptote. So let's draw that again. That's a bit better. And this equation has the equation y squared over b squared minus x squared over a squared equals 1. So this equation here, you can see the y is prior to the negative sign. Here you can see the x is prior to the negative sign. And this will indicate to you whether my hyperbola is left and right of my origin and of my asymptotes, which has x first, or whether my hyperbola is above and below my asymptotes, in which case y is first. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.